So we have these 4 topics left. This is about the myofibrils and the sliding filaments. So, what is a regulatory protein which binds to Ca2 plus to allow tropomyosin to be moved? We should know that it is troponin that binds to Ca2 plus and it allows tropomyosin to be moved. When action potentials occur and they lead to sufficient motor end plate potential of a muscle fiber, the concentration of calcium rises to a level where nearly all of the troponin is bound to calcium. Tropin, when bound to calcium, will remove tropomyosin from the actin filament and expose the myosin head binding side. This allows contraction to occur. So once troponin is binded to Ca2 plus, this allows tropomyosin to be moved. So there's tropin and there's troponin, and we need to know that when the action potential occurs, so you want to move a muscle, right? The action potential reaches the motor end plate potential of a muscle fiber, and from the nerve, the motor end, like there's enough action potential that reaches to the motor end plate, and that concentration of calcium rises to a level where nearly all of the troponin is bound to calcium. So troponin is what attaches to calcium. But tropin, when bound to calcium, will remove tropomyosin from the actin filament and expose the myosin head binding site. And we first need to know, just a second. What is it here? We have the filaments. So this should be here troponin, because when it says it's bound to calcium, it's the same as here. Then we have tropomyosin, which is a thread-like regulatory protein that binds to actin at the myosin binding sites and effectively blocks the active site, preventing myosin head actin interaction. So there is a myosin head and actin interaction that, if they have interaction, that will result in the contraction or the opposite. So when tropomyosin is bound to the actin at the myosin binding sites and effectively blocks the active site. So when it's bound to the myosin binding site and it blocks the active site, it is preventing the interaction, and that interaction prevents contraction. Cool. There's a power stroke cycle. The coupling of the energy produced from ATP hydrolysis to the conformational change of a protein. In layman's terms, this is how we take the energy from ATP and use it to shorten our muscles, to lift things and show off our biceps. So the power stroke is the coupling of the energy produced from ATP hydrolysis to the conformational change of a protein. In layman's terms, this is how we take the energy from ATP and use it to shorten our muscles, to lift things and show off our biceps. So how do you take the energy from ATP and use it to flex your muscles? It's with the power stroke cycle. It's when the energy produced from ATP hydrolysis is coupled to the conformational change of a protein. So the structure of the protein changes, which is coupled with the energy produced from ATP hydrolysis, and that is the power stroke. Now, actin is contractile protein, which composes the bulk of the thin filament. It contains the site recognized by myosin heads. And so we know that it is not a regulatory protein like troponin or even tropomyosin. When they have tropo at the beginning, it means, as a prefix, it means that it is a regulatory protein, right? But actin is a contractile protein. It means that it is contracting, and this composes the bulk of the filament, the thin filament. Actin is actin, and bulk of the thin filament is actin, and it contains the site recognized by myosin heads. That's where the myosin head and actin interaction takes place, right? There's tropin, and again we see it here. So troponin should be different than from tropin. Tropin is bound to calcium. When it's bound to calcium, it will remove tropomyosin from the actin filament and expose the myosin head binding site. So we should not get confused with the different binding sites here. There is one tropin that is bound or unbound to the calcium. So when it is bound to the calcium, it will remove tropomyosin from the actin filament. So when this is bound, when tropin, so they have reverse relationship, right? When tropin is bound to calcium, the tropomyosin head is not bound to the actin filament. So when tropin binds to calcium, the the myosin head is not bound to the actin filament. So it will be removed and expose the myosin head binding site. So when the binding site of the myosin head is exposed, this allows for contraction to occur. Then you have contraction, right? If you want to stop the power stroke cycle, you must remove calcium. So in order to stop the power stroke cycle, you must remove the calcium. It does make sense on the first glance, because when you don't have the calcium, the tropin is not binding to anything. So the tropomyosin head is bound to the actin filament, and it avoids it from moving, right? It prevents it from moving. Now we have the sliding filament theory, which describes the histological process of striated muscle contraction on the sarcomere. So the sarcomere has this thing. So yeah, sliding filament is basically all these things. We have sliding filament, we have striated muscle contraction, and we have sarcomere. So what does describe the histological process of striated muscle contraction on sarcomere? Is the filament theory and sliding filament theory. And what is the sliding filament theory describing? It is describing the histological process of striated muscle contraction on the sarcomere. So the striated muscle contraction is happening on the sarcomere, and the histological explanation of that is the sliding filament theory. Now we have the thin filament, which is made of actin, tropomyosin, and troponin. So thin filament is made up of the actin and tropomyosin and troponin. Interesting. And the thick filament is made up of myosin. Nice. So myosin is the only substance that makes the thick filaments, but thin filament has three main substances that make it. It's actin, it's troponin, and tropomyosin. Now we have the steps of the power cycle, which are important, very important. You can see here the picture too. So we have the tropomyosin as the blue circles. And then we have troponin on tropomyosin, and we have the calcium. So when troponin is bound to calcium, it should avoid the active site of myosin head. Oh, there is an active site over here. and there is a myosin head. So the myosin head is not bound. Now when the calcium but why is the calcium still here? Shouldn't it be unbound when the tropomyosin is attaching? We'll see. So the first step is the troponin bound to calcium removes tropomyosin, which exposes the active site on actin. Right. So the active site on actin is there in so these circles, blue circles, is actin. Tropomyosin is what is it's like the backbone, the yellow line. So when troponin is bound to calcium, the active site of actin is not interacting with tropomyosin head, with the myosin head. It removes the tropomyosin, which exposes the active site on actin. Removes tropomyosin, whatever that means. And then step 2 is that the myosin head binds to the active site, forming a cross bridge with actin. So step 2 is that the myosin head attaches to the active site, and this forms a cross bridge with actin. Remember that this is called cross bridge. And then step 3 is that the power stroke occurs, meaning the myosin head moves towards the center of the molecule, and ADP plus PI phosphate or inorganic phosphate are released. So when the power stroke occurs, because the myosin head was attached to the active site of the actin, the myosin head moves towards the center of the molecule. So you can see that the myosin head is moving towards the center of the molecule. Now in the bigger picture, we need to see where is the center of the molecule. Where is the center of this whole actin, basically, right? The thin filament. And ADP plus inorganic phosphate is released. The myosin head remains bound to the actin active site, even in the contracted state. So when your muscles are contracted, your myosin head remains bound to the actin site, right? This is a low potential energy state. So your energy state is low. When you are contracted, your potential energy state is low. If you are contracting things, a new ATP molecule binds to the myosin head. A new ATP molecule then binds to the myosin head, causing it to detach from the actin active site. So we have something as like the ATP, a new ATP. Immediately when it attaches to the myosin head, it detaches it. So when calcium is bound, when troponin is bound to calcium, you can see that it avoids the myosin head to interact with the active side. But as soon as uh, so apparently the troponin and calcium binding removes tropomyosin. So tropomyosin is removed and it exposes the active side. Interesting. So it all starts with the active side being exposed. You can see that here that the active side is exposed. And when the new ATP attaches to the myosin head, it detaches the myosin head from the actin active side. So the actin and myosin are now separated. And then the last step is that the ATP hydrolyzes, turning into ADP plus inorganic phosphate, and uses the energy from this hydrolysis to cock the myosin head, so it is ready for the next power stroke cycle. This is a high potential energy state. So when ATP uses its energy and turns into ADP and an organic phosphate, it is in a high potential energy state where the cycle repeats, where then you have it's so when ATP hydrolyzes, it turns into ADP and inorganic phosphate. It uses this energy from this hydrolysis to cock the myosin head. What does it mean? The myosin is cocked when ATP hydrolyzes. And this is a high potential energy state. Now we have no ATP means that so when no ATP is there, it means that the myosin head is attached, right? It can never dissociate from actin, so there would be constant contraction. This is what causes rigor mortis upon death. Ooh, so when you die, your muscles become contracted. All this ATP. That's why in the cadaver lab, the muscle of the cadavers was fully contracted, because there is no ATP, there is no energy generation, and that means that the myosin could never dissociate from actin. When action potentials occur and lead to sufficient motor end plate potential of a muscle fiber, the concentration of calcium rises to a level where nearly all of the troponin is bound to calcium. Tropin, when bound to calcium, will remove tropomyosin from the actin filament and expose the myosin head binding side. Oh, so that's why you need calcium for this whole thing to work. When tropin is bound to calcium, then the active sites are exposed, and that allows the myosin head to attach and for the whole contraction to occur. Interesting. Let's do the third last topic, solubility. What hormones, which are polar, dissolve readily in the blood? The peptide hormones. When they reach the target cell, they must bind a membrane receptor. They act on a variety of cell locations once they're finally in the cell, or they signal downstream reactions to happen without ever entering the cell. Think GPCR. So GPCR is a G protein coupled receptor, and when peptide hormones reach the target cell, they must bind to a membrane receptors, right, just like GPCR, and they act on a variety of cell locations once they're finally in the cell. So they act on different cell locations when they're in the cell, and they signal downstream reactions to happen without ever entering the cell. And they have this cascade of downstream reactions without entering the cell. Right. It's GPCR. I've studied that to an extent. When traveling through the polar blood, lipid soluble hormones require a protein carrier or a micelle slash vesicle. So when you are traveling through the polar blood, and blood is polar, sure, it's like liquid, it's like water, so it has hydrogen bonds, makes sense, it is polar. Lipid soluble hormones require a protein carrier, yes, because they are lipid soluble, and lipid is not polar. Lipid has these long chain fatty acids that are non-polar, and once they reach the target cell, so once the lipid soluble hormones reach the target cell, they don't require a cell membrane receptor. So when they reach the target cell, they don't require a cell membrane receptor because they can easily pass the cell membrane, right? They dissociate from their protein carrier and go straight on through this plasma membrane and bind to receptors on or inside the nucleus to influence transcription. So the hormones bind to the receptors on or inside the nucleus. And that's interesting. So they either bind to the receptors on the nucleus or inside the nucleus, and they go for transcription. But the peptide hormones, they just needed to attach to, they can easily go through the blood, but they will attach to a receptor on the surface of the plasma membrane because they cannot go through plasma membrane, and they cause a chain reaction downstream. We have the hydrophobic effect, which is, hydrophobic means that it is against water. And what does this hydrophobic effect explain? It explains why proteins fold with hydrophilic amino acids on the outside and hydrophobic amino acids on the inside. So why do proteins fold in the first place? You need that unfolding for, I believe, translation. Why do you need proteins? You need proteins to um, like proteins have different functions, right? Some of them are structural proteins, some are globular proteins, some are like hormones, right? And which amino acids are hydrophobic and which ones are hydrophilic? Some are like hemoglobin, right? Where would you expect to find a hydrophobic one? Folded inside the protein or on the outside? So hydrophobic ones means like nonpolar, right? And you expect them to be like the lipid soluble hormones. You expect them to be um, so you explain so you know why proteins fold with hydrophilic amino acids on the outside. So yeah, hydrophobic amino acids should fold on the inside and the hydrophilic ones on the outside. Because if you're hydrophilic, you're more like water, and water cannot pass through the plasma membrane because it's polar. And so you can fold. The folding thing is a different concept, but we can ask, why do proteins fold? And also, what are the functions of proteins? The plasma membrane is usually considered, so we know we have receptors and channels that are also proteins. So other than receptors, channels, carriers, what else? Structural, what else? Enzymes, what else? If anything comes, we'll ask it later. Oh, we have hormones. The plasma membrane is usually considered nonpolar. Sure. That's why also large steroid hormones can freely diffuse through the plasma membrane, but small polar molecules like ions cannot. They must use a transporter. Steroid hormones bind to a nuclear receptor. Sure, they need either receptor on the nucleus or inside. They are nonpolar, so they dissolve straight through the nonpolar plasma membrane and freely diffuse through the cytoplasm, all the way to their target structure, usually a nuclear factor. We have peptide hormones that bind to membrane receptor, and they are polar, so they cannot freely pass through the plasma membrane. We have ions that are added, but they don't change the equilibrium, are called spectator ions. Oh, I have never heard that before. Ions that are added, but they don't change the equilibrium, are called. So by equilibrium here, are we talking about the concentration or the charge equilibrium? So I assume it is the charge equilibrium here. So what are spectator ions and why do they not change the equilibrium? Increasing temperature decreases gas solubility in a liquid. So when you increase temperature, your gas solubility in a liquid decreases. Interesting. You're upping the heat, so everything is trending toward a gaseous state anyway. So the reverse relationship between gas solubility and increasing temperature is that because you're just it makes sense, like when you're upping the heat, everything is turning into gas anyway, so your gas solubility, the gas is basically escaping, the gas solubility decreases. The Henry's law states the solubility of a gas in a liquid, which is directly proportional to the partial pressure of that gas over that liquid. So the solubility of a gas in a liquid is directly proportional to the pressure, the partial pressure of that gas over that liquid. AKA, if you increase the pressure of the gas over a solution, imagine something physically pressing down on the gas above an enclosed liquid. It will yield to that pressure, dissolving into the liquid. It's almost like shoving the gas into the liquid, as crazy as it sounds. So if you increase the pressure of the gas over a solution, imagine like you press down on the gas with like a hydraulic presser, and the liquid is enclosed. It's in a closed system. It will yield to that pressure. Interesting. So we're here saying that the pressure is basically the priority here in everything. And when when you're pressing, the gas dissolves into the liquid. So like it's crazy because how can a gas get shoved into the liquid? If the liquid is water and you're shoving oxygen, how do the oxygen molecules go in between the water molecules? Into liquid through with pressure. So what we're, by the way, this is not filaments anymore. Why the proteins fold? This is something else, right? This is solubility. I don't know why the hormones are here, but And we have always soluble, so we have nitrates, ammonium, all alkali metal, group 1. They are always soluble. The MCAT will occasionally sneak in a question involving a common soluble or insoluble compound and expect you to know their solubility. Almost always insoluble. We have carbonates, phosphates, silver, mercury, lead. Now we need to know these, so we need to make sure that we know all of them. So nitrate, ammonium nitrate, and the group 1 metals, they're all soluble, and the insolubles are carbonates, lead, silver, mercury, phosphates. A negatively charged solution is going to reduce a positively charged substance better. This is in contrast to the like dissolves like mantra of hydrophobicity. And about hydrophobicity is that like dissolves like, sure, but we have something opposite here, where a negatively charged solution is going to reduce a positively charged substance better. That is a deep one. So we have, let's say, a proton, a positively charged substance. That's too small. Let's say we have a lysine or arginine or asparagine, and it is positively charged. So you want to reduce that. Gain of electron is reduction, right? So you want to give it electron. We know that the positively charged substance loves electron, right? It must love an electron. So because it can, the electron can attach to it, right? So a negatively charged solution is going to reduce the positively charged substance better. Totally makes sense now. It's also good to note that it is in contrast to the hydrophobicity law, the hydrophobicity mantra, that like dissolves like. But however, we're talking about a solution that is reducing that. So reduction is something else. The almost always insolubles we talked about were lead, silver, mercury, and then we have the carbonate and phosphate. Sure. All these, unless paired with something from the always soluble list, are insoluble. So the MCAT will occasionally sneak in that question. Always soluble or nitrate. So if you have, for example, I don't know, like a silver nitrates, then that becomes soluble, right? Is there a silver nitrate? And if yes, is it soluble? By soluble, I think we are referring to soluble in water, right? So water is hydrophilic, it's polar. We are trying to see if something is polar so it can be solved. Nitrate should be soluble because it has the nitrogen. It can interact with, make dipole interactions with the hydrogens and hydrogen bonds. Ammonium has nitrogen too. And all of the alkali metals are reactive in water, right? Like dissolves like describes how well substances dissolve in regard to polarity and or hydrophobicity. This is in contrast to acids, bases, and electrostatics, which work best and are attracted to each other. So the polarity and hydrophobicity is for like dissolves like is for polarity or hydrophobicity. So the contrast, the opposite, is for acids and bases and electrostatics. So acids are attracted to bases, really? Or for electrostatics, it makes sense. Protons and electrons, they're the law of each other. Okay, there's only this left. What is stoichiometry? Stoichiometry is like balancing out the chemical equations, right? So we have person mass. If this is not a question yet, we should ask it. Stoichiometry. What is stoichiometry? What is person mass? What percentage of the mass is accounted for by X element? So take water for example. I could ask what the percent mass of hydrogen is in water. So hydrogen is 1 grams per mole and there's 2 of them, so total of 2 grams per mole. The total mass is 18 grams per mole. So divide the proportion by the whole and you get a little less than 0.1 or 10%. So 2/18 to be exact, which is 1/9. And yeah, 1/9 is a bit less than 0.1. You want to see what's the percentage of 1/9? 1/9. Isn't it 0.9? Maybe 0.09, I mean 9%. We have then the molar mass, which is how much mass is in 1 mole of that particle. The MCAT usually gives you this value for complex compounds, or you can use the periodic table to add up the molar mass. Yes, we know that. For example, oxygen is 16 grams per mole, right? When finding the limiting reagent, you should use grams or moles. For limiting agent, you should use moles. So if we're given 220 grams of ferritin and 150 grams of water, at first glance it looks like the water is going to be the limiting agent because it's less, right? But if we convert them to moles by dividing their mass by the molar mass, we see that we have 3.94 moles of iron and 8.3 moles of water. Then I take into account their coefficients. For every 3 moles of ferritin, I use 4 moles of water. The way I like to do it is by dividing the moles by my coefficients. So I can essentially run 1.31 reactions with the amount of ferritin I have. But I can run my reaction 2.075 times with the amount of water I have. So therefore, ferritin is the limiting reagent. So we have coefficients. So for every 3 moles of ferritin, I use 4 moles of water. The way I like to do it is by dividing the moles by coefficients. So I can essentially run 1.31 reactions with the amount of ferritin, because 3.94 divided by 3 is 1.31, and we have 2.075 times with the amount of water I have. So you can see here that you have 8.3 divided by 4 is 2.075. So therefore, ferritin is the limiting reagent. Then we have, so what is the molar mass of water and how do you calculate it? So 18 grams per mole is the molar mass of water. Sure, yes. And you calculate it by adding the molar masses of its constituents. Yes, we have hydrogen and oxygen. The mass that is listed on a periodic table is the molar mass. How many grams are in 1 mole of that element? Yes. So the mass that is listed on a periodic table is the molar mass. We have molarity, so moles of solute per liter of solvent. It is a measure of concentration. How many moles of a solute you have in a solvent. It's molarity. And a mole of bricks is going to have more or less or equal mass than a mole of diatomic oxygen. So the brick, the 1 mole of the brick, so brick has more grams per mole than diatomic oxygen, right? Number of particles in a mole is not going to change, but the mass does. So the mass of each particle in the brick is heavier, is more than the mass in the gas, for example, diatomic oxygen. That's why the number is never going to change. The number of particles in a mole, they're not changing. But the molar mass, the mass is changing. A mole is 6.022 times 10 to the 23 particles of anything. So it's just an amount. So 6.022 times 10 to the 23 of bricks, it's going to be enormous. It might be like the whole planet, who knows. But definitely, so it definitely has more mass. It's Avogadro's number. And we have the last topic. We have the Schachter-Singer two-factor theory of emotion states, that first the stimulus occurs, then our body experiences physiological arousal, and cognitive interpretation of that event. So the combination of the physiological arousal with the cognitive interpretation tells the brain which emotion to feel. So you see a bear, your muscles tense, and your heart begins to race while your brain asks itself, is this situation scary or am I just getting excited? Once the brain realizes you should be scared of a bear, those signals get interpreted as the emotion of fear. Nice. So, for the Shockster Singer two-factor, we have the stimulus occurring, first step. Second step is that our body experiences physiological arousal and cognitive interpretation of that event. So you see the bear, first step, stimulus. Your muscles tense and your heart begins to race, physiological response, while it's two factors at the same time. Why is this situation scary? Is this situation scary or not? And then you realize you should be scared. The second theory is the James Long theory. So the first the stimulus occurs, sure. Then our body experiences physiological arousal, and that physiological arousal is interpreted by the body as an emotion. So now you see a bear, your heart begins to race, and your brain says, my heart is pounding, so I must be experiencing fear. In the first one, the brain, as a response, like while your heart was racing, it was asking, is this a scary or unscary situation? And because your brain realized that you should be scared of a bear, those signals got interpreted as the emotion of fear. But in the James Long theory, you do see the bear, you do get the heart rate increased, and then your brain says, oh, my heart rate, due to the physiological response, arousal, I am scared, I am experiencing fear. And you can see the different stuff here, right? So the first one should be the Shockster Singer theory. The Shockster Singer should be the second one. Or let's see, what is the Cannon bar theory? It is the stimulus occurring, then our body experiences physiological arousal and emotion simultaneously. So this is the Cannon bar. It's the order is not correct here. So when you see a bear, oh, Canon, there's a Canon camera. When you see a bear, that signal gets sent to your thalamus, which directs the signal to your limbic system. You experience fear, and to your visceral afferents. You experience the physiological effects of fear at the same time. So the other ones, there was a cognitive label 2. I believe the third one here is the label that your brain puts on it, right? Oh, so if your brain is so that physiological response is experiences emotion. This should be the first one. James Long should be the first one. But the labeling thing comes with Shockster Singer. two-factor, right? And for Cannonbar, you just see the burr and the signal gets to your thalamus, which directs the signal to your limbic system. You experience fear, and then to your visceral afferents. So you it goes to both. You experience the fear and you experience the heart rate at the same time. How can you prove these? Theories of emotion. Which theories of emotion is correct? Give me examples and comparisons. 15. Shakhtar singular two-factor theory versus Cannon Bard versus James Long theories. Boom. So now we're kind of done with this section. We might need to go over these again, as I have, however, done them frequently. And these ones are, I have to go through the central dogma. So for tomorrow we have the central dogma. Central dogma. Yeah, these. We have the classic conditioning. That should be fine. I have to go through these, the enzyme kinetics. Enzyme kinetics. The ETC for sure. ETC. Exons, introns. Sure. In glycolysis, I did not go through this. We did go through Krebs cycle, however. We have, we did the hemoglobin oxygen curve, yeah. Cool. I'll see y'all tomorrow, and for now, peace.